guys, it's Newomaster, and welcome back to another redstone video. In this video I will be explaining how the Dabble algorithm works, as I have been requested by a couple people to do so. I've built a different BCD decoder over here that I will be using later to demonstrate how the algorithm works. This is a sequential one, so I don't have a clock hooked up to it, but I can just hit the button over and over again and it will do the steps of the algorithm so you can see it in action. But first of all, I'm going to explain how the algorithm actually works. So the algorithm, as I said earlier, is called the Dabble algorithm. Basically what you do is you take a number, the binary number, like that number, and you shift it left into a empty register for the BCD number, and shift it as many times as you have binary bits. So for this example right here that I've set up, I would shift in 5 times. And if the digit in any of these BC digits is over 4, then you add 3. So it doesn't make a whole lot of sense now, but it will make a lot more sense once I'm finished explaining it. So I'm going to go ahead and perform the algorithm on these numbers here that I've set up in this example. First thing you do is shift. So I'm going to call this first shift. I'm going to shift that first number in. So it'd be like this. So I just shifted that number 1 to the left. So the 0 here, and there's 5 ones between those right there. So right now the value of this number in BCD is 1. Now I can shift again since this isn't greater than 4 yet. So second shift, and that would be equal to 3 in BCD now. And that would be equal to whatever that is in binary. Now, since this is still not greater than 4, I can shift again. And then that shifts over as well. But now, the ones digit of this BCD number is greater than 4. So I have to add 3 as the algorithm says. So I'm going to add 3 to that ones digit. So ones digit greater than 4, add 3. So 1, 2, 3, 4, and 3 plus 7 is 10, so that would be 10 in binary. And then same thing over here still because I haven't shifted again yet. Now you would think that I would have to add 3 again because that's 10, but you have to shift again before you do that again. So you can only add 3 once, and then you have to shift again. So this would be the fourth shift. Fourth shift. I don't want to spell it right now. I'm lazy. So that would be 0, 1, 0, 1, and then 1, 0, 0, 0, like that. So I shifted that 10 into the tens digit right here, and then I also brought in another 1 from over there, as usual. Now this is over 3 again, or over 4 again, right here in the ones digit. So you have to add 3 to the ones digit again. Ones digit over 4. Add 3. There we go. So what was that? 10 or 5. So 0, 0, 0, 1, then 8, because you added 3 to 5, we get 8, and this is the same over here again. Now last shift, fifth shift, is the 5th shift, and there's 5 bits. So shift we do 0011, so we shifted that in, and then the next number would be 0001, bringing that last 1 in from the binary digit. So now the binary digit is all zeros, and we have our BCD number, which is 31 in BCD 31, and since we started with 11111 in binary, which I know to be 31, calculate it if you want to. This is indeed correct. Woohoo! Now, why does this work? Good question. To answer that, I'm going to set up a little example over here. Anything greater than 4 when you shift it over. So like, say I have 5, when you shift it over, it's greater than a BCD, one single BCD digit can handle. So, say I have a number like 1, if I shift that over, the BCD digit can still handle it, right? It's a 2. 2, if I shift that over, BCD digit can still handle that because it's a 4. I have a 3 over here, and I shift that over, it becomes a 6. BCD digit can still handle that because it's 6. And if I have a 4, I shift that over, BCD digit can still handle that because it's 8. But if I have a 5 and I shift that over, the BCD digit can't handle that anymore. So what can I do? What number can I add to 10 right here that would make it carry over to the next digit over here? 10. What number can I add to that? Well, since the maximum you can have here is 15, if I add 6 to 10, it would carry out. So if I add 6, it would be that. But we want to add before shifting, because if we add after shifting, we can't accommodate a new digit coming in to the left. So we add 3 instead, because when we shift, we multiply by 2. So if the number is greater than 4, we add 3 to it, so 5 plus 3 would be 8, and then when we shift, it becomes 10. Woo, magic. So that's pretty much why this works. Now, time, make it day. Day. Oh my gosh. Times set 1. There we go. Now, how do we implement this into redstone? I'll show you how. This here is a direct implementation of the algorithm that just shifts using, these are repeater lock shift registers here. Each of these decoders here finds, since there's only a certain number of, you don't really need an adder, there's only a certain number of combinations that are over 4. In fact, there are only math 5 of them that are over 4, between 0 and 9. So I can just use a decoder and some ROM underneath. So for this decoder, there's a ROM right underneath the decoder, and numbers that are over 4 are coded to be the different number to add 3. So like this last one here, a 9, add 3 to that, and it becomes 12. And over here I have this torch here, which powers the 8 and 4 lines, which becomes 12. It comes over here. Now, it's kind of hard to see, but in here I have more repeater locks, which continues the shift register, and you can see that the ones digit goes over to the 2s in the next stage of the shift. So after this gets shifted in using the repeater lock shift register, it goes up here to the next digit. So this is just shifting and changing the number based on what the decoder says. Now, I'm just gonna do the example that we did before with that would be 1, 1, 1, 1, 1, like that. But now this is 8-bit. Just to keep that in mind, this is 8-bit. So it's going to have 3 extra button pulses before the numbers start appearing, just to shift. So the first button pulse is just to save it into the repeater locks, and then I get rid of these levers. Actually, I'm gonna put a button on the other side of that block, right here. Okay, so shift 1. Nothing's gonna be appearing on the output yet. Shift 2, still nothing appearing. Shift 3, still nothing appearing. Now on shift 4, stuff is going to start appearing on the output. So this is equivalent to the first shift of the one that I did. So the first shift right here, just a 1. You can see that. Now I'm going to shift again, and it'll be 3 here, which is what I had in my calculation as well. Now when I shift again, it's also the same thing as I had. Now you're not going to be able to see it adding the 3. Well, you can see it down here. This is where it's adding the 3, and then it would save that into the repeater locks and shift that. So it's going to save and shift at the same time. So what you see in the next pulse will be that. So 000100101. That. So boom, and there you go. Now I was on the 4th shift, so 1 more. Again, this is going to add 3. You can see it right here. This is the 8 that it added. And then shift again, and we have 31. It worked. And to do it with the combinational stuff, it probably deserves its own video because it's slightly different. Well, the algorithm's the same, but how you implement it is kind of wonky. So I'll probably make another video on that eventually. Probably not for a while, because frankly I'm tired of doing BCD stuff. But yeah, I'm gonna update the world download so you guys can take a look at this for yourself, because BCD is something that you learn from experimenting it yourself. I'm gonna try my hardest to explain it, but most of it is figuring it out for yourself. And this thing right here is just a clear. You activate that and save it, and then the number gets cleared after you deactivate that. So thank you for watching my video all the way through. It was probably pretty boring to watch, honestly. But yeah, thanks for watching, and I'll